Characteristics of logarithmic functions. Hello, everyone. To begin our lesson on the characteristics of logarithmic functions, let's first ground ourselves in what we have already learned. In our previous sections, we established a fundamental relationship. The logarithmic function is the inverse of the exponential function. This means they essentially undo each other. Now, to truly understand how logarithmic functions behave, it is not enough to simply know the definition. We must carefully analyze their specific mathematical properties and examine their graphical representation. By doing this, we can visualize how the function moves and where it is restricted, which we will explore in detail in the coming slides. Finally, to keep our analysis consistent and clear for this discussion, we will assume that the base, b, is greater than 1. This specific condition will allow us to identify the standard growth patterns and characteristics of the logarithmic curve. The domain of the logarithmic function. Now that we have established that logarithmic functions are the inverse of exponential functions, let us dive into their specific characteristics, starting with the domain. First, let us clarify what we mean by the term domain. In simple terms, the domain refers to the set of all possible input values, represented by x, for which the function is defined and produces a real result. To understand the domain of a logarithm, we must perform a step-by-step analysis, starting with its definition. Recall that the equation y equals log base b of x is mathematically equivalent to saying b raised to the power of y equals x. Since we are considering a base b that is a positive number, any power y we apply to it, whether that power is positive, negative, or 0, will always result in a positive value for x. To illustrate this, let us look at an example. If the base b is 2 and the power y is negative 3, then x equals 2 to the power of negative 3, which is equal to 1 over 8. Even with a negative exponent, the resulting value of x remains positive. This demonstrates that there is no real power y that can make b raised to the power of y equal to 0 or a negative number. Consequently, we reach the conclusion that the domain of the logarithmic function is the set of all positive real numbers, which is denoted as r+. Mathematically, we express this by saying x belongs to the open interval from 0 to infinity. It is very important to note that logarithms of 0 or negative numbers are undefined in the set of real numbers. Now that we have defined the allowable inputs for the function, we will move forward to the next slide to examine the possible output values, known as the range. The range of the logarithmic function. Now that we have established the domain, let's move on to the range. In simple terms, the range refers to the set of all possible output values, which we represent as y. Let's analyze this step by step to understand why the range behaves the way it does. First, consider what happens as our input, x, becomes very large. As x increases toward infinity, the output, y, also continues to increase without any upper bound. On the other hand, let's look at the opposite end. As x approaches 0 from the positive side, the value of y becomes increasingly negative, dropping further and further down. Because y can take on any value from negative infinity all the way to positive infinity, we can see that the output is not restricted in either direction. Therefore, we can conclude that the range of the logarithmic function is the set of all real numbers, which is denoted by the symbol r. Now that we understand the possible inputs and outputs, let's identify a specific key point that every logarithmic graph will always pass through. The key point, the x-intercept. Now that we have established the domain and range of the logarithmic function, let's identify a key landmark on its graph. Regardless of the base we are using, every logarithmic function of the form y equals log base b of x will always pass through one specific point on the coordinate plane. To understand why this is the case, let's perform a step-by-step analysis. Let's consider what happens when we set our input x to 1. When we substitute this into our equation, it becomes y equals log base b of 1. To solve for y, it is easiest to convert this logarithmic statement back into its exponential form. This gives us b raised to the power of y equals 1. Now, recall a fundamental property of exponents. Any non-zero base raised to the power of 0 is always equal to 1. Because of this rule, the only value that y can take to make this equation true is 0. Consequently, we can conclude that the graph of any basic logarithmic function will always pass through the point 1, 0. This point serves as the x-intercept of the function, providing us with a reliable starting point before we examine the overall behavior and growth of the curve in the next section. Behavior of the function. Now that we have established that the graph always passes through the point 1, 0, let us move on to the overall behavior of the function. When we discuss the behavior of a function in mathematics, we are essentially describing how the output value, y, changes as the input value, x, increases. Let us analyze this step by step. For a base b that is greater than 1, as the value of x increases, the power y required to produce that x also increases. However, there is a nuance here that you should notice. While the rate of growth slows down as x becomes larger, the function never actually stops increasing. It continues to climb, albeit more slowly, as it moves to the right. Therefore, we can conclude that the logarithmic function is an ever-increasing, or, more formally, a strictly increasing function. Understanding this steady upward trend is crucial, as it sets the stage for our next topic, where we will examine what happens when x decreases and approaches 0, leading us to the concept of the vertical asymptote. The vertical asymptote. Now that we have discussed the domain, range, and the x-intercept, let's examine a critical structural feature of the graph, the vertical asymptote. First, let's define our terms. An asymptote is a line that the graph of a function approaches closer and closer as it extends, but it will never actually touch or cross that line. To understand why this happens here, let's perform a step-by-step analysis. Recall from our discussion on the domain that the input, x, must be a positive number. But what happens as x gets extremely close to 0? For example, if we substitute values such as 0.1, 0.01, or 0.001, we find that the output, y equals log base b of x, becomes a larger and larger negative number. If you were to visualize this on a graph, you would see the curve drop sharply downward into the fourth quadrant. However, there is a strict limit here. Since we established earlier that x must be strictly greater than 0, the value of x can never actually reach 0. Consequently, the curve can never touch the y-axis. This leads us to our conclusion. The y-axis, which is mathematically represented by the line x equals 0, serves as the vertical asymptote for the logarithmic function. Understanding this boundary is essential, as it highlights the fundamental difference between logarithmic and exponential functions, which we will explore further when we discuss their symmetry in the next slide. Symmetry and the inverse relationship. Now that we have analyzed the domain, range, and the vertical asymptote of logarithmic functions, let us examine a more profound geometric relationship. Specifically, we will look at the connection between the natural exponential function, y equals e to the power of x, and the natural logarithmic function, y equals the natural log of x. To understand this relationship, we must recall that these two functions are inverses of one another. This implies that if a point, a comma b, lies on the graph of e to the power of x, then the corresponding point, b, a, must lie on the graph of the natural log of x. In the study of coordinate geometry, swapping the x and y coordinates of a point is equivalent to reflecting that point across the diagonal line where y equals x. Consequently, we can conclude that the graphs of y equals e to the power of x and y equals the natural log of x are mirror images of each other, reflected across the line y equals x. This symmetry provides a visual confirmation of the inverse properties we have discussed throughout this lesson. Having established these theoretical characteristics, we will now move forward to see how these properties are applied in a real-world context, such as the pH scale. Real-world example, the pH scale. Now that we have explored the theoretical properties of logarithmic functions, let us look at a practical, real-world application to see how these characteristics function in science. A prime example is the pH scale used in chemistry to measure how acidic or alkaline a solution is. If you look at the formula on the slide, the pH value is calculated as negative log base 10 of the concentration of hydrogen ions. Let us break this down using the properties we have already discussed. First, consider the domain. As we established in our earlier analysis of the logarithmic domain, you cannot take the logarithm of a 0 or a negative number. In this chemical context, since the concentration of hydrogen ions can never be negative, the domain is restricted to positive real numbers, which perfectly aligns with the mathematical requirements of a logarithmic function. Next, let us discuss the concept of logarithmic compression. In slide 5, we noted that while logarithmic functions increase, their rate of growth slows down significantly. This is incredibly useful here. Because of this slow growth, a massive change in hydrogen ion concentration, for instance, a drop from 0.1 to 0.0001, is compressed into a small, manageable scale of pH values, such as a change from 1 to 4. This makes the data much easier for scientists to work with. Finally, let us apply what we learned about inverse relationships. Just as we saw that the natural log is the inverse of the exponential function, we can reverse the pH formula to find the actual concentration. To find the concentration of hydrogen ions from a given pH value, we use the inverse exponential form. The concentration of hydrogen ions equals 10 raised to the power of negative pH. Understanding this application helps bridge the gap between abstract algebra and physical science before we move on to our final summary and common pitfalls. Key takeaways. Now that we have explored a real-world application with the pH scale, let us consolidate everything we have discussed so far. This slide serves as a summary of the essential characteristics of logarithmic functions. First, let's review the domain. As we established in our earlier analysis, the domain is the interval from 0 to infinity. In simpler terms, this means that only positive real numbers can be logged. You cannot take the logarithm of 0 or a negative number. Next, we have the range. The range consists of all real numbers, spanning from negative infinity to positive infinity. This indicates that the output of a logarithmic function is not restricted and can be any value. Regarding the x-intercept, remember that every basic logarithmic function always passes through the point 1, 0. Moving on to the asymptote, the y-axis, which is defined by the equation x equals 0, serves as the vertical asymptote. The graph will get closer and closer to this line, but will never actually touch or cross it. In terms of growth, as long as the base b is greater than 1, the function is strictly increasing. While the rate of growth slows down as x increases, the function continues to rise indefinitely. Finally, let's recall the symmetry. The graph of y equals the natural log of x is a mirror reflection of the graph of y equals e to the power of x, reflected across the diagonal line y equals x. This is a direct result of them being inverse functions. Please keep these key takeaways in mind, as they will be crucial for understanding the common pitfalls we will discuss in the final slide. Common mistakes to avoid. To wrap up our lesson, let's go over some common pitfalls. It is very important to be mindful of these errors when solving problems. First, let's discuss the mistake of logging 0. A common error students make is attempting to calculate the log of 0. If you recall our discussion on the vertical asymptote, the graph of the logarithmic function approaches the y-axis, but never actually touches or crosses it. Because the function never reaches the point where x equals 0, the log of 0 is mathematically undefined. Secondly, be careful with negative numbers. it is easy to forget that the domain of a logarithmic function is strictly restricted to positive real numbers. For example, if you encounter an expression like the log of -5, remember that this has no real solution because you cannot take the logarithm of a negative value. Finally, let's address the confusion regarding asymptotes, because the exponential and logarithmic functions are inverses of one another. As we saw when discussing their symmetry across the line y equals x, their asymptotes are mirrored. Do not confuse the asymptote of the exponential function, which is the x-axis, or y equals 0, with the asymptote of the logarithmic function, which is the y-axis, or x equals 0. Keep this distinction clear in your mind to avoid graphing errors.